All right, so we had some cyber contests. The National Cyber League awards came out, and we won third place in the whole nation, so that's pretty awesome. A very good job of our students here doing this team. And we went and did the CPTC, and we didn't place in the top 3 there, but I'm very glad the students did it, and I think everybody had a really good time. And it's very good for them to get jobs, even if they don't win. You don't have to win to get a good job. Just being there will impress employers, as it should, that you take this seriously and you're in the top performer in cybersecurity. And it was a new team and we'll probably score better next year. But anyway, it was a very good event. I'm very glad people went. I had a good time, and I think all the people I was talking to there had a good time. I liked talking to the coaches and learned some new things. So that was a very good event. And there's another one coming up, CCDC. And I highly recommend people sign up for this. You do not need to be very advanced. And it is, we need a couple more people to make a team. So fill out that form if you're interested. And let's get on to the official stuff. This is where we start talking about iOS. And as I mentioned before, in the news section, one problem with this class about iOS is I don't have hands-on iOS projects because Apple is very, very restrictive about iOS devices, and you cannot run a nice, free, emulated iPhone the way we're running emulated Android phones. And I tried actually buying a bunch of used iPhones, but they're really old. And so anyway, we're only going to talk about iOS attacks this semester and not perform them hands-on. So I've demonstrated all the required hands-on projects and a lot of the extra credit ones. We're coming to the end of the semester, 3 more classes after this one, and that's it. So let's talk about iOS. One good thing about it is it's very much like Android. And I think Android came later and probably imitated iOS. iOS was the original. But anyway, if you understand Android, then iOS is going to be minor variations on the same thing. So we're going to talk about the security model and the apps and jailbreaking. And next time we'll talk about these other topics. So the iOS security model. You've got the secure boot chain, and it's really secure. That's why Axiom X took this course and then developed a new jailbreak, the first new one in 7 years, by defeating the boot up process, which is pretty heroic. But not that I taught him how to do that. I only taught him the bare fundamentals like you, and he went way beyond that. But anyway, and then the code signing we'll talk about, which is much, much better than Android code signing, which I've complained about a lot. It's pretty much a joke. The sandboxing, which is pretty much the same as Android. And their encryption is quite impressive. And we'll talk about the standard Linux mitigations that we talked about before. It has the generic mitigations that you find on the Mac OS and on any version of Linux these days. So here's the boot chain. This is really secure, and Android doesn't have anything like this as far as I know. In fact, most Android, at least most Android devices I think are not even encrypted at all by default. But this is the equivalent of secure boot. So they have a boot ROM, which is a read-only memory chip that you can't change, that starts it up, and that goes to this low-level bootloader, and then it starts iBoot, and that loads the kernel. And this is all secured. The boot ROM contains the public key for Apple's certificate authority, so it doesn't even trust the usual HTTPS certificate validation. It's got key pinning, essentially. It even knows what that certificate authority should be, so you can't fool it by any kind of manipulation of network traffic. And that is used to verify the low-level bootloader to make sure it is matching the signature, so it hasn't been modified at all. It's genuine code from Apple, signed by Apple. That's the low-level bootloader. That then finds the iBoot image, and it verifies its signature and makes sure that it's signed. And if that fails, it boots into recovery mode so you can restore this part, but it won't boot up and let you use the phone because something is wrong. This is why you can't put a rootkit on an iPhone, and it's why you can't put a rootkit on a device using secure boot. In principle, you can. There's always some way, but it's much, much more difficult. You would have to defeat these mechanisms that are really quite powerful. And then iBoot loads the kernel, which shows the normal user mode environment with the icons you can click on and all that. But those things there are many layers of cryptography there protecting it. Now, the iPhone, for many, many generations, I think everything since the iPhone 3S has had a secure enclave. I'm not quite sure how far back it goes, but it's very far back. The secure enclave is the equivalent of a trusted platform module in a Windows machine. This is a coprocessor which performs cryptographic operations, and it has the cryptographic keys in the secure enclave, and they are not present anywhere in the address space of the main processor. The main processor has to send data to the secure enclave and say, please decrypt this, but it can't get at the key. And therefore, no malware no malicious app on the phone could steal that key. And that's exactly the same thing with Windows machines. Encrypted with bootlocker. The key is in the trusted platform module, and no malware can steal it. The only known ways to steal it are the cold boot trick, where you get it out of RAM by freezing the RAM, and there's another one where you dissolve the trusted platform model with acid and reach in with a tiny needle to suck it off the pins inside there, which is pretty heroic. You have to do crazy things like that. The fact is, it's really hard to steal any cryptographic data off an iPhone. It's very secure. And so that's got your key management. It's also got your touch fingerprint data, and I imagine the face print data, although I'm not sure. So it is technically the ARM trust zone. That is, the ARM processor has this thing called a trust zone, and it's partitioned from the main processor. So even if you have full control of the kernel, you still can't get in. Even if you jailbreak the phone and put on whatever you want, you still can't get the secrets out of it. That's the idea. Now, like I said, nothing is perfect. There's always some kind of attack, and this is the attack against the ARM trusted zone, the cache grab. And this because it shares cache memory with kernel processes. There are sometimes ways to trick it into putting some information in the cache that you can get, which will give you some information about the secret keys. So nothing is perfect, but this is not a common attack. I've never heard of anybody actually breaking into an iPhone with it, but it's worth remembering that no protection is ever perfect. There's always an attack against every defense. All right, so the processes are signed, and this is much better than Android. Now, like Android, you have to have it signed, but remember, in Android, you can just use self-signed signatures, which are what you call snake oil signatures. They don't really prove much of anything. But this is not true. Only code signed with a trusted signature can run. Now, normally that means code signed by Apple. However, as you know, you can add another trusted certificate to a device, and you can do that with iPhones too, but you do it in a provisioning profile, and that should be signed by Apple. So you have to get Apple's permission to do that if you want to trust another store, and that's something a company might do because they might have proprietary apps that they want to use on their company iPhones, but they do not want to put them in a public store. So it's the kind of thing you do there. But again, you have to convince Apple to trust you enough to do it. This is why iPhones have essentially no problem with malware, and you don't have to worry about most security problems. There's no way to put antivirus or firewall on them. You can't get it, and it won't run it, and you don't need it because you can't put proprietary code on it. You can only put stuff from Apple, and Apple cleans their store quite effectively. So there's very little malware in the store. It happens a few times, but when somebody puts malware in the store, they know who every developer is, and they block them forever, and you can never sell any more iPhone apps, and that's a dreaded punishment, enough to stop people from doing it, because you make real money from iPhone apps. People make their living that way, and they don't want to get banned by Apple, so they don't do it. So Apple also bans self-modifying apps because they audit an app to make sure it's not doing bad things, and they do not want to let you change your app later. If you want to change it, you have to make a new version and submit it again to Apple for review. Uber got in trouble for this. Various app companies got in trouble trying to modify their app and slide past the Uber. If you read the Mindfuck, I think, the book about Uber, which is really interesting, Uber actually tried breaking Apple's App Store rules. And when they got caught, they said, we could just ban Uber from the App Store, and where would you be then? And that would be the end of Uber, and so they got in shape pretty fast. So you can have private APIs where you load code from your own server and run it, and they won't let you do that. You can have download and install executable code from anywhere. They won't let you do that either, because then you could put code in there that Apple didn't get to review. Yeah?
But their ability to take down a business basically by taking them off the App Store, wouldn't that make them kind of a monopoly?
Absolutely. This is a very good question. Doesn't that make them a monopoly? It absolutely does. And it looks like the Americans, anti-monopoly people like Amy Klobuchar and Elizabeth Warren have been screaming about this for years, saying Apple is like a monopoly, and they own the phones and they own the store, and they charge a huge ruinous amount. They charge 30% of all the money in the store. And I remember Kindle at one time, the first version of the Kindle app had a link to go to Amazon and buy the books, and Apple made them quit. You have to buy it through us and pay us 30%. And any attempt to evade that will kick you out. And that's pretty exploitive. They've recently lowered that to like 15% and even less in some cases, because they're really afraid of punishment by the US government for this. But the Europeans just passed a law that's really going to punish it. They just passed a law outlawing all these walled gardens. They say you have to let people load apps from elsewhere, but they haven't finished determining which things it applies to, but I think we can guess who it applies to. So it looks to me like, just like GDPR changed how everybody's handling personal data, I think the European laws against this monopoly stuff are probably going to break up Apple's monopoly. And Apple's the richest company on earth. A couple of years ago, they were richer than the entire U.S. government. They're making so much money with this monopoly stuff. It's incredible how much money they're making. And various governments, indeed, would like to take them down a peg and take some of that money away, which does seem pretty justified. However, it's absolutely true that if you get an iPhone, it's not got any malware, you don't have to worry about it, and it works pretty well. They deliver value to the consumer, but they get a lot of money for it. I remember when I switched to using Macs, I said, this is now you realize you're going to be it's like owning a luxury car. You're going to have to pay a lot of money forever for everything. You accept an expensive life, but you get a good product. So anyway, so the apps are separated from each other. They run in a sandbox, but they all run as the same system user. Remember, in Android, they each run as a different user account. Here they run all with the same user, but there's something called the XNU sandbox kernel extension, which separates them, so they can't go into each other's directory. So I think it amounts to about the same level of security. You can't break out of it without a kernel exploit. So the Apple sandbox has been through many versions. Originally, it was called Seatbelt, and then it was updated to the App Sandbox, and now it's considered even stronger. More and more evolved. Apple's been going through many versions. The first version of the iPhone ran everything as root, and there was no app store. All it had was code Apple put there. There was none of this stuff. But then when they had the store, then they had the main root account and a non-root account to run all the apps from the store. So it's got permissions, and every modern version of iOS, like Android, asks for permissions to use the media, the microphone, the address book, and so on. All right. And everything is encrypted. Like I say, every iPhone, even remotely in use now, everything is encrypted right from the beginning, which is really good, and it's a shame Android doesn't have it. This is why you can sell your iPhone. There's a setting in the settings to return to factory defaults, and when you do that, it erases the key, and all your data is scrambled beyond redemption. And a forensic company tested this. They bought 100 used iPhones on eBay, and they tried to get data off them. They did not get any usable data off any of them. So you can safely wipe your phone and sell it. Nobody will get the data. That is not true of Android phones, except for some of the high-end models that now do have encryption. But the point is, you have to have encryption on by default right from the start before you ever type any data in, or some of that data will be sitting in there unencrypted, even if you encrypt it later. And Apple's been doing that, so it's really quite effective. They know where the key is, and they wipe out the key, and that's why reverting to factory defaults is in fact instantaneous. It doesn't take any time, because all it does is erase the key. And you're back. Yeah.
But I assume companies like Samsung have that now too, right? Like the big Android providers.
That's what I've heard. I've heard that the Samsung, if you get a high quality Android, they've had this for the last few versions too. Yeah. But the cheap Androids don't have it. Or at least they don't have it on by default. You'd have to turn it on because they feel like it drains their battery life. Apple also has really strong rules about wasting battery life on your apps. Android doesn't. So a lot of apps just drain your battery because they can't control what you do, because it's got more freedom, so you're putting in apps from everywhere, and the apps do not have to be approved by Google, so you can just write a crappy app and people use it and drains their battery. So you can encrypt things, you can encrypt files and keychain items. The key is derived from a passcode, like we've done in the cryptography course, how to derive a key from a passcode, and they're inaccessible. The encrypted devices are inaccessible. Even when the device is on, if it's locked, those items become inaccessible. There are several levels of encryption available in the Apple system. So here's some generic exploit mitigations that you'll find in every Linux-type box these days, and even in Windows mostly these days. Write or execute is the main one. If you would allocate a memory region to be used by an app, you have to specify whether it's writable or executable, and it cannot be both, because you don't want to have any area. It's very common that you're able to write to memory because of a buffer overflow or something. And if you do write to memory, they don't want you executing that code. That was how the classic buffer overflow exploit worked, and this is how they prevent it. You have ARM's execute never feature, which means you can mark a page of memory non-executable. And that's the game. And by the way, this is something I do not think is true of Windows machines. I don't know about Android. Because in Windows machines, you can change the permissions of something. You can write to it and then make an API call to change the permission to make it executable later, but apparently not on the iOS. So that's pretty cute. Anyway, this is data execution prevention is what they call it in Windows, and every modern operating system has it, the only exception being the Raspberry Pi. Raspberry Pi, at least version 3, has read-write execute on every memory segment, and I was pretty horrified to find that out. That is way out of date. That's the way we did it in like the 90s. Nobody should be doing that anymore. Anyway, So now the cure for non-executable memory, which if you take our exploit development next semester, we'll do this. If you have non-executable memory, you can still make an exploit, but you can't run any code. So what you do is you inject a bunch of addresses, and then you jump to like a return instruction that's sitting in memory, and it loads that address in from the stack. You write the stack a bunch of addresses, then you hit execute return. A return sucks an address off the stack and goes there. And so it sucks the next track and next address. So you build your exploit out of code you can find, and you just put a list of addresses there. It's the equivalent of like cutting up a newspaper to make a ransom note. A couple letters here, a word there. And that's return-oriented programming. And there's tools that do that. By the way, a lot of defenses are coming out on this. There was one I heard on Pulse Security podcast a couple weeks ago. There's an app, Microsoft has developed a lot of these. They're developing you'll have a series of keys stored in like the registry on Windows that says where you're supposed to enter every routine. And you can only enter the official entry point. You can't jump in a couple of instructions from the end to use just a couple of, it's a pretty good idea. But that is not in common use in any operating system yet. And so this works. That's how you do it when you have non-executable memory.
But, yeah. Sorry, when you do that, you can't write your own code. You have to use the code that's already there.
All you're doing is reusing code the developer put there. And it has to be not jumping around in memory either. You have to find some code that's there that you can find, and you know where it is, and then you find a series of addresses that will patch together instructions to build what you want to do. And we'll do it next semester. There are tools that do it. It used to take like an hour to build it. Now it's pretty fast. But of course, what you do is you build code that will allocate some new memory that's executable. Just a generic thing is all you got to do. Got to figure out how to make one Windows API call. But still, it sounds impossible, but it's not impossible. There are tools that do it. But they're building defenses against that. So, this is the life of the exploit developer. They keep building more defenses, and you keep doing it, just like the cops get bigger guns and the crooks get bigger guns, and on you go. So ASLR is another real important defense where instead of just using the next block of available memory when you launch an app, it recuses random memory to launch every app in, so you never know where you are. And that means even if I want to do return-oriented programming, and I find some code to use, I don't know where it is. It's jumping around every time. So it makes life harder. So that's also applied in iOS. Now, there are some weaknesses in ASLR, and by the way, the same thing is true of Microsoft's implementation, the simplest one being not everything is randomized. There is some code that is always in a predictable location, so you can find stuff there to use. Also, you can sometimes find memory disclosure bugs. This is why the low CVE score vulnerabilities, like 2, a memory information disclosure, some people say, ignore the CVE score. Every vuln is a vuln. Because if all it does is let you read a couple bytes of memory, that might be the address of something you need. And then you've fouled up ASLR. That's why, but technically that alone doesn't give you code execution, but it could be helpful into doing it. Another thing, only apps that are compiled with this feature, position independent execution, can be randomized. So old apps compiled without it cannot be relocated. And the same thing's true of Windows. And next semester we'll see if you run old code, it doesn't randomize. So even though the operating system is trying to protect you, it can't, because you have to recompile the code with another section called the relocation section to allow this. And if it's not there, you can't relocate it because the code itself has absolute addresses to jump to the modules. So anyway, there's other apps that put parts of it, like the linker and such, at the fixed address. So, that's just like in Windows, the same thing's true. Not everything is randomized. If everything was randomized, that would really slow down your attacks. Anyway, then there's stack canaries. This is to stop the classic stack overflow. The buffer overflow is where you have an array of bytes, and you're able to put in more bytes than you're supposed to, so you overrun it. And if you overrun it, you eventually get to the return pointer, which is where it's going to go when it returns. And then you overwrite that, you gain control of the box, because you can cause it to execute code at an address you choose. And if it's executable, you can jump back into the stack and execute those bytes you inserted. So you can just put in data and run it, which is awesome. And to prevent that, you use stack canaries. At the end of every stack frame, between the data for this frame and the control data, like the return address, you put a random number. And every time you return, it verifies that random number has not changed. And to make sure that nobody's been overrunning and trying to overwrite things. And that is really pretty effective. They call it a stack canary, and that's also present in iOS and in every other modern operating system.
can you not read the randomized number when you overflow? I mean, when you
In principle, you could, but see, he's asking if you can read it, the randomized number. The problem is it's chicken and the egg problem. You're trying to gain code execution. You don't have code execution yet. If you could run code, you could read that number. Now, maybe and if you could inject code, but you can't run the code until after it tries to return from that routine. So it is quite effective. That's a very good question, though. Another thing you could do is see if you can find it somewhere, but they hide it places. You'll see it. And we already saw it a few times this semester in the 126 class. But anyway, it's a good question. These things are hard. Now, in the old days, sometimes this number was actually predictable. That's one way they got it, but now it's not. They're getting pretty good with these. All these defenses are getting pretty strong. All right, and so your apps. There's native apps, browser-based apps, and hybrid apps. This is one big thing about security in iOS. The apps are not written in Java, so they are not distributed with effectively their source code. They're like compiled apps you'd run on Windows. So they're actually much harder to reverse engineer. So they're intrinsically a lot stronger. So the most common type are written in Objective-C or Swift, then compiled to real assembly code to run on the ARM processor. And the symbols are removed, so you don't have the names of the variables and names of the routines like we've seen in Android. So reverse engineering these things is like reverse engineering Windows malware, which is a lot harder. So there's also browser-based apps that just run in the browser like a web page, and that's an option. They're just effectively web apps being viewed in a browser. And there's hybrid apps where you build a native code wrapper, and that connects to the browser. This is like the WebKit thing that we talked about in Android. But, all right. So they're all, like I say, almost everybody gets all their apps from the App Store, and therefore you have to make an Apple developer account. They have to know who you are and keep track of you. And then you have to send all your stuff to Apple, and they decide whether they like it, and then they sign it. And you get a developer certificate. Now, you can get a developer certificate, and you can test it. You can go up to 100 devices and test an app just with your developer certificate, but there are restrictions to that. But you can't put it anywhere where the whole world can use it without going through Apple's process to get it in the official store. And they're quite strict about letting people in. Very few people have found flaws in the App Store testing and found a way to sneak an app in, but you can only do it once. Charlie Miller was an NSA hacker, and he came out of there and started doing all this mobile app, and he stuck malware in the store, and they canceled him forever. You can't do any more research involving putting apps in the store anymore. They're not messing around. They really have no sense of humor like the TSA. You mess around with them, they hate your guts forever. So there's also something called enterprise distribution, like I said before. If you want to make an app for the people in your company and you don't want it in a public store, there is a way to do that. But you have to convince Apple that you're a legitimate business and you have a Dun & Bradstreet number. I don't know quite what that is, but it's some kind of proof that you're a legitimate business. You basically have to convince Apple that you are a real corporation and therefore they're trusting you with this. And in fact, it can lead to trouble, and it has led to trouble. Once those enterprise certificates get out, they're like Windows enterprise keys to activate Windows, which also keep leaking out, and people use them to activate pirate versions of Windows. So some of these got out, and what people found, they have an expired developer certificate, so you can change the system date back into the past so it's not expired anymore, and then you can run code. So that's how the Game Boy emulator runs, and that's how one of the jailbreaks runs, by using an expired developer certificate. So anyway, apps, remember Android apps are just zip archives, and so are iOS apps. It's an IPA archive. It's just a zip archive containing the same kind of stuff, something called payload, compiled code, artwork, metadata in a plist file. And every app has permissions. In the old days, every app had permission to everything on the phone. But now, of course, it does the same thing Android does. You have all these classes of data, and you have to give it permission to access each of these things. It will ask you, can this app access your contacts and so on, just like everybody does these days. So you know what your apps are doing in general. And you'll see a list here. You can determine which apps are allowed to reach your contacts and take them off the list if you don't like. Everybody has these granular permissions these days, which is a good idea. Although I think almost no users are actually energetic enough to pay attention to this. They just agree to whatever and put on the app. But in principle, you could turn it off if you wanted to. So iOS, you have location information, for example, and so you can say never, only while it's in use, and always. We've seen this on our phones. I see this all the time. Before, older versions of iOS didn't have that. It was all or nothing. Now everybody has this. And so then there's jailbreaking. We've been rooting the Android phones with Magisk, an exploit, and you can do the same thing on iOS. They call it jailbreaking in that case, getting root permissions on your iOS device. And the main reason people do it is to get pirate software. Cydia is the unofficial app store that has all the pirate stuff, pirated copies of games, and all kinds of hacking tools. Metasploit, scanners, everything is in Cydia. The code development libraries, C compilers, you can write your own stuff. Get full control of your iPhone. You're off the map, and so that's the point. And you can then, the one popular thing was tethering. I don't know if this is true anymore, but for a long time, Apple didn't let you tether your phone through the iPhone data connection, and they limited it and are charged for it, and now you could get an app that would do it in here for free. I guess I'm paying a bit to use mine officially. I could get a free version here if I jailbroke my phone, but I haven't done it because, I'd like it to actually work. Because once you jailbreak it, it's risky. Now all your defenses are gone. It's risky. You're weakening the security. Now you're allowing unsigned code to run. You're going to put random crap from Cydia on there. So this is like downloading stuff from God knows where and running it on your phone. So you lowered the security of the phone. And there's a bunch of malware that infects jailbroken phones. There's almost no malware that affects an unjailbroken phone, but there's been a series of malware that attacks jailbroken phones, primarily because when you first jailbreak your phone, you open the root account and the default password is Alpine. And most people don't know that and they never change it. So it's got a known password. So it's incredibly easy to infect it. So iKey would rickroll people by just playing that irritating Rick video. And here's one that made your phone into a bot for remote control, iKey.B. There's one called Baby Panda that hooked functions to steal your Apple ID and password. And there's a variety of these that infect jailbroken phones. Jailbroken is the word. All right, so there's three kinds of jailbreaks. The most desirable one is an untethered one. You modify the phone, and now it's permanently jailbroken. You can restart it, and that's what you do. For example, I've done it for some of my friends that wanted to connect to an European service. They need to escape the American service. So this is the button you want. This means your phone is permanently jailbroken. Now it's off the map. But tethered jailbreaks means you need a computer to start the phone. You cannot start it without a computer anymore. The most common ones I've seen are semi-tethered ones, where you can boot it from a computer to get into the jailbroken mode, but if you boot it without the computer, you get back in the old non-jailbroken state. All right, and of course, you voided your warranty. If you need help from Apple and they find out you jailbroke your phone, they just hang up and you say, get lost, we'll have nothing to do with you, you scum. And I remember, when I first jailbroke my first iPad, I thought, well, I'll just make an iTunes backup, and if I foul it up, I'll go back to that. And then I put on stuff, and I needed to change my MAC address to connect to the college network at that time. And I found a MAC address changer that was for 3 versions back iPhone, not the iPad, and I put it on there, and it crashed it. But after that, I was able to change the MAC address. So I put on all kinds of horrible stuff until it was all fouled up. Then I tried to restore from the backup, and I've learned something important. I thought an iTunes backup was like a Windows 7 image backup, every byte on the disk. It is not. It is a copy of all the folders that Apple thinks you should be messing with, not the system. So when you restore it, you are not restored to your original state like I thought. There's no going back. That's why they don't want to hear it. If you jailbreak your phone, don't talk to us because you can foul it up and we don't make any tools that will save you back from that.
Yeah, I remember when I was younger, I jailbroke an old iPad and
Yeah.
software updated on accident and it never turned on again.
Yeah.
I tried to bring it in.
Yeah, mine got screwy problems and there's no way back. Yeah. I thought, oh, it's fine. I got a backup.
Yeah, I was trying to make an excuse in the store about it somehow randomly happened, and they did not.
Yeah, that's why Apple's not messing around when they tell you don't jailbreak your phone. If you do, you're on your own. Use at your own risk. Anyway, but it was fun. I learned a lot. It's educational, but I didn't need that device too much. If you really need that device, if that's really your phone, don't jailbreak it until you're pretty damn sure you know what you're doing. By the way, the process was scary as hell. I had it was like a $1,000 iPad, and first you put on the jailbreak, you run the exploit, it turns black, just totally dead. Then it comes up for 10 seconds, then the message fills with green error message, then it stops, then it comes back with upside down tiny red letters, error, 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 and I said, boy, I'm glad I've used Linux before, I'm used to this shit. You'd be pretty terrified. It really looks like you're ruining it. But it was fine for a while until I put on too much bizarre crap that had no business being there.
It's a very suspicious process for sure.
Yeah. Anyway, Jailbreak 3, this was pretty fun. V3, I remember this one. It was great. They had a PDF exploit that would exploit the PDF reader on the phone, the default one. And all you had to do is go to a website called jailbreakme.com, and there's just a button you go, swipe, and that's it. It jailbreaks your phone. It was awesome. And what they do is jailbreakers find these. They have secret mailing lists, they plot it, then they pick a time, then they tell people, and it's only good for like a week because Apple immediately patches it. But for that week, you can just jailbreak your phone effortlessly, and that was cool. So this used an integer signedness issue and a ROP payload. So it was able to, because of a wrong type of a variable, it was able to trick it into writing to memory it shouldn't be writing to. So it was pretty good. Then there was the evasion. Without memory corruption, it just found logic bugs. There was a lockdown D service that you could use to change file permissions, and there was a USB driver that would let you call arbitrary functions. So they were able to download some code, make it executable, and run it with kernel permissions just through a series of logic flaws, which is another way to do it. And anyway, so if you want to build your own testing environment, which we've done in previous semesters, but not this semester, then you get a phone, you jailbreak it, install Cydia, and then you can install OpenSSH, and now you can connect over Wi-Fi or USB. And like I said, by default, the mobile is the non-root user, and root is the root user, and both of them have Alpine as the password by default. So if you leave the Wi-Fi turned on and you don't change that password, then you're just asking for it from the whole world. What's better, you got to change this, or make it so you only listen over USB. And then, of course, nobody can get in without physical access to your phone, which is better. But the best thing would be to change that password to something else. Anyway, so Cydia is the store that has all the open source apps. It's put up by a guy named Sorek. And they sell, some of them charge money too, so I think it's a real business to make that stuff. It's all sort of piracy and semi-illegal, but that's where you go. And there's a package of tools you can put on to get all the tools, and then you can run apt-get on your iPhone and just install stuff like you would on Ubuntu. It's pretty cool. And you got Apple's tools to parse, assemble, and link Mach-O binaries. Linux executables are ELF, Windows executables are PE, and Apple executables are Mach-O. It's the format of them. And so that's part of the iOS development toolchain. There's a thing called OTool that lets you open object files and see what's in there. So you can see the class and method names and libraries and symbols and header information, so you can get some information. It's the start of reverse engineering and binary analysis of iPhone executables. And you can get the symbol table here, and LiPo is pretty awesome. By default, most Mach-O binaries, and by the way, most Android apps now have multiple versions for multiple platforms, because you might have a 32-bit phone or 64-bit phone, and so they call those fat binaries, and LiPo will pick one version out, making them skinny again. So GDB is the debugger you use for Linux debugging. We'll use it a lot next semester in 127. For some reason, Cydia doesn't have a good version, and you have to get Radari's version if you want it to actually work. GDB is really powerful, but pretty hard to use. We'll use it quite a bit next semester. We'll learn the most important simple 10 commands of it. It can do anything, but it's kind of hard to use, like WinDebug. Here's Apple's code signing tool, and here's Sorek's code signing. So you sign it with this if you want to verify an Apple signature, or if you can sign it for Apple, but you're not going to have the private key to make a genuine Apple signature, or you sign it with this to put it on Cydia. And then you can install IPA. The normal app installation goes to the install D, but that verifies the Apple signature, so you use IPA installer as the one that installs stuff without verifying the signature, which is, of course, what you want to do to run unauthorized code. And so the file system, you can now explore the whole full access, which is why all security researchers really need jailbroken phones, so they can go into the Apple software and the folders and find out what's going on in there if you want to do things like develop a new jailbreak. And you can get to everything. And you connect to over USB typically to do it, just like we've been doing Android with USB debugging. There are apps you can use to explore it, but if you connect over the USB or through SSH, then you just get a Unix command line terminal like we've had, and you can totally get access that way. So on a jailbroken device, you'll see applications. System applications are here, third-party applications are there, and then you got all the goodies that you'll see. If you're doing the forensic class, we're doing forensic analysis of images of iOS phones, and you have voicemail, SMF, videos, pictures, email, contacts, and all that stuff. This is what forensic people care about. Proof of what you've been doing on the phone, because it's part of a crime. We need to know who you were sending messages to and stuff.
Is this what people like? When people try to make new jailbreaks, do they go back to old ones and explore kind of the code that's on the phone and see what still will be exploited?
Well, let me repeat the question. The question is, when people are making new jailbreaks, do they go back and read all the code from old jailbreaks? Not the ones I know. The one I know best is the Checkmate jailbreak, because that was developed by one of my students, and he talked to me while developing it. Not that I am responsible in any way. He's way beyond me. But what he did was, he took Apple's latest patch and he reverse engineered the patch to find out what they were patching. And he found out that they were patching a flaw in the heap allocation function in the ROM that cannot be changed. The heap allocator could be tricked into allocating the wrong amount of space for a heap object, so he was able to write 1 byte more than he should, and the last byte had to be 0. He managed to take over the whole phone with that, which is pretty impressive. It reminds me of this Monty Python when they say, attack me with this banana, be as vicious as you like. But he was able to take over the whole phone with that. And he explained it to me, and I didn't really understand it. But anyway, that's what you do. That's typically what you do. The point is, because it was in the hardware, they can't fix it. All the generations of hardware of that type are vulnerable forever. And so that's why it was really valuable to people. Now researchers can just get that phone, jailbreak it, now they can get in the phone. Because for like 7 years, you couldn't get in. And so the researchers can't really examine what Apple is doing.
How could he see those patch notes, though?
How can what?
How could he see that? Like, how did he know that they did that patch? Like,
Oh, well, they do put out updates, and you can get them from the website and stuff.
oh,
Yeah,
okay.
so you get the update file, and then your version engineer see what it's doing. Same thing's true of Microsoft. So Microsoft says there's Patch Tuesday, followed by Exploit Wednesday. Because when you put out the patch, that's a blueprint telling everybody how to attack you. Because all you got to do is look and see what they changed. And it's pretty simple to figure out what the vuln was. And that's what he did. It wasn't all that simple. He paid $5,000 and got the full version of IDA Pro and spent like a month researching bit by bit what it was doing with a huge monitor, but he did it. It's not impossible anymore. That's the technique I've heard used most often. But I don't know how they develop these others, but I don't think they develop very much from each other. The jailbreak community is just super experts about how the iPhone works. They understand what every step is, what every executable is, and what it should be, just like Mark Russinovich, that wrote the Windows internal books. He knows everything about Windows. Like when he got the Sony rootkit, Sony wanted to mark machines so you can't make a pirate copy of the music. It'll only play on that one machine. And they did it by putting a rootkit on the machine. And when he got a Sony music and played it, he instantly spotted it's a rootkit because he knows exactly what's going on in Windows. And he wrote these tools that reveal all the system processes and API calls and everything. He can immediately see, wait, that's a rootkit. In fact, he has a standing offer. He'll clean malware off anybody's window for free. Because for him, it's that easy. He can just look at, oh, I see what that's doing. And your jailbreakers are like that. They really understand every detail of every step, and they know, where the weak spots are. Yep. All right. And of course, the same thing's true of the military in every nation, their cyber military, and the API groups. They've got people that can develop new stuff, and they're buying 0 days too. Although jailbreakers, I don't think are buying them. They might be selling them, but they're not buying them. Anyway, but the jailbreakers are people who've chosen to take these powerful exploits and donate them to the world. So they're sort of hobbyists, they're sort of altruists, giving away stuff, because jailbreaks would be worth $1 million if you sold them to a military or to a crime group. Because they could make a standing offer. It's multiple $1 million. The NSA will pay you and other groups if you can get into an iPhone with a 0-click exploit. And that can be done. That's what that company was doing I was talking about before, the Israeli company. NSO Group will sell you that stuff to like Saudi Arabia and stuff, and they can just get right in everybody's phone. And the Russians can do it, and the Americans can do it, and the Chinese and North Koreans, they've got their secret ways by the same process. Researchers find it, and they don't tell anybody. They make the weapon, and they use that weapon against their enemies. Eventually it leaks out, but for some period of time, you can get on everybody's stuff, and there's no defense. Anyway, so plist files are the binary format where you store just the information, and you can use the PL-util to make it readable. So this is the configuration files, basically equivalent of the Windows registry for iPhone apps and for Mac OS apps. And you got cookies. For some reason, they have binary cookies, which is news to me. All the cookies I've seen are like base 64, and there's a special app to read the binary cookies. And of course, SQLite databases, just like Android. So those are more features of how iOS apps work. So let's look at a Kahoot, which I got here, 2A. And I figured out how to turn off the irritating noise that was irritating remote listeners. So my noise when I delete files was loud, and I found out a way to make it quieter, I think. Yeah, not seeing any chat today. All right, but there are people. All right, good. All right. All right, so what step will fall into recovery mode if it fails? Yeah, the LLB. The boot ROM, if that fails, you can't even get going, but the LLB can fall back into a recovery mode to give you some way to fix it. The low-level bootloader. All right. All right, which one started out called seatbelt? Yep, that's the sandboxing. All right, so which mitigation uses XN? That's non-executable memory. Intel's corresponding feature is called NX. So, you know, there's not a lot of imagination in these names. Non-executable memory. All right. All right, which mitigation do you bypass with ROP? Non-executable memory. If you can't execute memory, you just put in a bunch of addresses to point to code you can't execute. So it doesn't actually execute any of the code you put in, it's just used as addresses. It does not deal with ASLR because ASLR means you can't tell where things are, so you don't know what addresses to put in. All right, and what was the first iPhone worm? Yep, iKey. All right. And what's the default root password? It's Alpine. All right. All right. I think we know who JC is. Look like real initials. And you're home. Good. All right. So, stop the recording.